You ever stop to think about what it takes to get clean water from your tap, or just to keep the lights on? Well, behind the scenes of our entire modern world, there's this invisible universe of automated systems working 24/7. They're the hidden machinery running our most critical infrastructure, and today, we're going to pull back the curtain.
Everything from a power plant to a car factory starts as a blueprint, just an idea on paper. But how do you get from that drawing to a real-world physical operation that actually works? The answer? Industrial Control Systems, or ICS. Think of them as the digital nervous system that bridges that gap, automating and managing the physical world all around us. So how do these things actually work? Let's dive in.
All right, here's our game plan. We'll kick things off with the big picture, why these systems are so incredibly important. Then we'll get right down to the fundamental building block of all this automation, what's called a control loop. After that, we'll check out the specialized computers that act as the brains, zoom in on the real workhorse called the PLC, and finally, see how it all scales up to run huge operations.
So, when we say critical infrastructure, we're not kidding. We're talking about the absolute foundations of modern society. Water treatment plants, the power grid, oil and gas pipelines, you name it. All of these sectors totally depend on these automated systems to run safely and efficiently. And because they're getting more and more connected every day, understanding how they work is more important than ever.
Okay, at the very heart of all this complex automation is one simple challenge. How do you automatically control something physical? Could be the temperature in a chemical reactor, the pressure in a pipe, whatever. The goal is to keep that thing right where you want it, without a human having to stand there and watch it all day. And the solution to that puzzle is the control loop. So, first things first, we need to know what we're trying to control. In the lingo of ICS, this is called the process variable, or just PV. It's any physical thing you can measure that changes: temperature, pressure, flow rate, the level of liquid in a tank. If you're trying to control the temperature in your house, the room's temperature is your process variable. Simple as that.
Okay, so we know what we're measuring. Next, we need a target. What value do we want that process variable to hit? That's our set point, or SP. It's the goal. So back to our house example, the temperature is the process variable. If you set your thermostat to 72 degrees, then 72 degrees is your set point. The entire job of this system is to make the PV match the SP.
Now, this diagram looks a little technical, but it's really the universal blueprint for how this works. It's a continuous cycle. First, a sensor measures the actual process variable out in the real world. That measurement gets sent back to a controller. The controller's job is to compare that measurement to the set point and ask, are we too hot? Too cold? Based on the answer, it sends a command to an actuator, which is the thing that physically changes the process. It's a constant loop. Measure, compare, correct. All right, that block diagram is a bit abstract, so let's make it real. Let's say our job is to keep the liquid in this tank at a perfect temperature. We've got our physical pieces here: a burner for heat, a gas line, a valve to control the gas, a temperature sensor sitting in the liquid, and a controller box to run the whole show.
Now we can connect the dots back to our blueprint. The temperature of the liquid? That's our process variable. The temperature sensor is, well, our sensor. The controller box, with its diaphragm and switches, is our controller. It's doing the comparing. And the gas valve is our actuator. It's the muscle that takes action, opening or closing, to change the process by adjusting the flame. See? It all maps perfectly.
This whole self-correcting cycle is what engineers call closed-loop control. The key phrase here is closed loop. It means the system is always watching itself, feeding its own results back into the decision-making process. This ability to self-regulate, to constantly adjust on its own, is really the magic that makes all of industrial automation possible. Now, our little tank example used a pretty simple mechanical controller, but the brains of modern systems are way more sophisticated. The jump from old-school mechanical relays and dials to digital, microprocessor-based computers was a total game-changer for the industry. It brought a level of precision and flexibility they could have only dreamed of before.
So you might be thinking, hey, it's a computer. Why not just use a regular PC for this? Well, you can't, and this chart shows why. The design priorities are polar opposites. In the IT world of office computers, confidentiality is king. You've got to protect the data. But in the industrial world, availability is everything. You absolutely cannot have downtime. You can't just tell a power grid to pause and install updates. A system going down isn't an inconvenience, it can be a catastrophe. These machines need to respond in real time, and they talk to punks and valves, not keyboards and mice. They're just built for two completely different worlds.
These special-purpose computers are usually called field devices. Why? Because they're installed out in the field, right next to the physical equipment they're running. The three most common types you'll hear about are PLCs, RTUs, and IEDs.
So let's zoom in on the most common and, frankly, the most important of these controllers, the PLC, or Programmable Logic Controller. If there is one device that is the undisputed workhorse of modern automation, this is it.
A PLC is basically a rugged, industrial-grade computer designed to do one job and one job only: control stuff. They were actually invented to replace these massive, complicated cabinets filled with clicking mechanical relays and timers. Instead of needing to physically rewire an entire panel to change how a machine worked, you can now just reprogram the PLC. It was absolutely revolutionary.
And if you were to pop the hood, the basic layout would look pretty familiar. You've got a main processor, you've got memory like RAM and ROM, you've got data buses. All the core parts of a computer are there. But every single one of those components has been hardened and optimized for the harsh, demanding life of an industrial controller.
And this is what one actually looks like. Check out this compact PLC. Notice what's missing? You're not going to find any USB ports, no monitor connection, no keyboard plug. Instead, you get these neat rows of screw terminals. The ones on top are for inputs. That's where you wire up your sensors. The ones on the bottom are for outputs. That's where you connect your actuators, the motors and valves. It's built for direct physical I/O.
Now, for bigger jobs, you use a modular PLC. And the name of the game here is flexibility. It's kind of like Legos for industrial control. You start with a rack, called a backplane, that supplies power and data. Then you just snap in the modules you need: a CPU, a power supply, and then whatever mix of input cards, output cards, or networking cards the job requires. You can build a perfectly customized controller for pretty much any task you can dream up.
Okay, so a PLC is the perfect brain for a single control loop or one machine. But what happens when your machine is an entire factory or a pipeline that stretches for hundreds of miles? A single controller just isn't going to cut it.
Right, so what do you do when the process is just too big or too spread out? You can't run a million wires from every single sensor all the way back to one giant supercontroller in a central room. It would be a nightmare. So how do you solve that problem?
Well, you do what engineers always do with huge problems. You break them down into smaller pieces. You divide the whole massive process into smaller, logical chunks. And then each one of those chunks gets its own dedicated local controller, like one of the PLCs we've been talking about, whose only job is to manage that one specific area.
Of course, now you have a new problem. You've got all these little brains running around doing their own thing. To make them work together like a team, you have to connect them. You network them together with a special kind of industrial network called a field bus. This lets all the controllers share data and coordinate what they're doing. A lot of times, you'll even have one controller acting as the master to orchestrate the whole symphony.
And this entire architecture has a name. It's called a Distributed Control System, or DCS. The key idea is right in the name. The control intelligence is distributed across lots of smaller controllers instead of being stuck in one big central brain. This makes the system way more reliable because if one controller goes down, the whole plant doesn't stop. And it lets you scale up to manage unbelievably complex operations.
So we've gone from one simple control loop to a massive, distributed network of computers that are literally running our world. They're powerful, they're essential, and more, they're being connected to the internet. Which leaves us with one final and really critical question. As the invisible machinery that controls our physical world gets more connected, how do we make sure it stays safe and secure?